Good morning, everybody. Welcome back to Linear Algebra. Plan for today is we're going to finally wrap up Standard 1. And then we're going to do the Standard 2. And then we're going to start talking about Standard 2, which is on vector algebra. As far as homework goes, we are going to have our first quiz on Standard 2 on Friday. That's right. We're going to have a quiz on Standard 2 before we've even finished talking about it. If you all are ready. Also, I should be careful what I write on. Did you all actually believe that? Also, I'm going to post some problems later today that are going on Canvas that'll be from the Standard 2 stuff in the book that we're going to be talking about. Mainly focusing on section of 1.3. We've got office hours today at 11 and at 1. Tomorrow at 10 and at 1. In the meantime, if anybody wants to come by and ask for their first retest, since we are finishing Standard 1 today, you are welcome to do so. So, if you want to do that, send me an email to let me know your comment. And then you can come by my office hours and I'll put you in the side room to do an alternate version of the Standard 1 quiz. And that can be your retest for the week.
Could we do that after Friday's quiz?
You could do... Does 11 o'clock work for you on Friday?
Yeah.
Then yes. Send me an email.
Yeah, thank you.
So I'm not planning on holding any office hours on Friday, but I'll be around at 11 o'clock for a little bit. So be happy to do it then. Does anybody have any questions or comments before we get started for today? Why was 6 afraid of 7?
7, 8, 9.
7, 8, 9. But why did 7 eat 9?
He's hungry.
Hungry. And 7 knows the importance of eating 3 squared meals a day. Okay, with that, I want to get back to finishing off Standard 1. So you may recall from last time that we talked about the row-reduced echelon form. I'm teaching linear algebra, not real analysis. Form of a matrix, where you take your matrix and you use elementary row operations to get your matrix in a form where if a row has any non-zero solutions, gosh, I was on drugs when I was writing this. If a row has any non-zero numbers in it, the first non-zero number has to be a 1. If a column has one of these leading 1s in it, then all other numbers in that column are 0. And finally, if a row has a leading 1, then every row above it has to have a leading 1 that is further to the left. So for instance, last time, we looked at an example of solving a system of linear equations that had this matrix that corresponded to our system. X minus 3y minus 5w equals negative 7, 3x minus 12y minus 2z minus 27w equals negative 33, and so on. And we were able to use our elementary row operations, multiply a row by a constant, swap 2 rows, add a multiple of 1 row to any other row, in order to get that matrix down into this form. And so we would say that this is the reduced row echelon form of that matrix. And what I thought we could start class off by doing today is I want to solve a system of equations once again by taking this system, negative 3x plus 6y plus 9z equals 12, x minus 2y minus 4z equals 10, and negative 9x plus 18y plus 30z equals negative 6. And I want to put this in, put that in a matrix, and then put that matrix in reduced row echelon form to see what we can find. And this will kind of be our last practice problem that we do from Standard 1 in class before we move on to newer and cooler stuff. So we put this in matrix form to start. We'll get negative 3, 6, 9, 12, 1, negative 2, negative 4, 10. and negative 9, 18, 30, negative 6. And our goal is going to be to use our elementary row operations, put this in reduced row echelon form. Go ahead and augment that matrix just to make it clear that it corresponds to a that particular system of equations. So what do you think would be a good first start if we want to get this in reduced row echelon form? If we want to ref it up.
Well, I would say you could swap row 1 and row 2.
Okay, that would get a number 1 in the top left corner of our matrix, which I think would be ideal to do. So let's do that. We could swap row 1 and row 2. And that's going to give us 1, negative 2, negative 4, 10, negative 3, 6, 9, 12. Bottom row stays the same. Yes?
To use the 1 to eliminate the negative 3 and negative 9.
Cool. How do we do that?
By adding, it would be 3 row 1 plus, replace row 2 with 3 row 1 plus row 2, and then replace row 3 with 9 row 1 plus row 3.
Yeah, I think that'll get our left-hand column into the form we want, where our left-hand column will have 1, 0, 0 in it. So if we do that, first row stays the same. Second row, let's see, negative 3 plus 3 is 0. 6 plus 3 times negative 2 is 0. 9 minus 12 is negative 3. And 12 plus 30 is, I believe, 42. And in the bottom row, negative 9 plus 9 will give us 0. 18 plus 9 times negative 2 is 18 minus 18 is 0. 30 minus 36 will give us a negative 6. And negative 6 plus 90 is 90 minus 6, which is 84. Gadzooks.
We can divide row 2 by negative 3.
Cool. Divide row 2 by negative 3. Or since I'm a multiplication man, I'll multiply by negative 1/3. If we do that, we'll get 1, negative 2, negative 4, 10. 0, 0, 1, negative 14. And 0, 0, negative 6, 84. I don't know if we're going to be able to get a leading 1 in our second column. Because if we would need one of these two rows to have our leading 1 in the second column. Can't be the first row. First row has its leading 1 in the first column. So what can we do from here? We want to get this in reduced row echelon form.
Could we find what z is and plug it into the first equation, shrinking the whole matrix?
Find what z is and plug it into the first equation. You want to take the route where we rewrite this as a system of equations at this point?
Yeah, as a 2 by 2 or a 2 by 3.
We could. I would prefer not to do that. What I would like to do is to just use our elementary row operations to get this in reduced row echelon form. But if we just wanted to solve the corresponding system of equations, we could certainly do that at this point and say from here z has to be negative 14, for instance. I think we could do something equivalent by, say, adding 4 times the second row to the first row to tell us something about x and y. So I think that's what I want to do.
You could also add 6 times the second row to the third row to
Okay, so add 6 row 2 to row 3. Sounds good to me. Let's see, top row. 1 plus 0 is 0. Negative 2 plus 0 is negative 2. Negative 4 plus 4 is 0. 10 minus, oh gosh, 28, 56. I think that's negative 46. 0, 0, 1, negative 14. Second row stays the same. And then the bottom row will add 6 row 2 to row 3. 0, 0, negative 6 plus 6 is 0. 84 minus 14 times 6. Let's see. 14 times 3 is 42. Times 2 is 84. 84 minus 84. Oh, hey. What else do we need to do to get this matrix in reduced row echelon form?
We would need to get rid of the negative 2, or get rid of the second column 0, because in the second row, your leading 1 needs to have. Never mind.
Retract it?
Yes.
What's your question?
It's in row echelon form.
Is it? If a row has non-zero numbers, the first non-zero term is 1. That's true for row 1. That's true for row 2. Row 3 doesn't have any non-zero number, so it's technically true for that. It is, as mathematicians would say, vacuously true. But the first non-zero term in the third row is a 1, because there aren't any non-zero terms to choose from. If the column has a leading 1, I count 2 leading 1s. All other numbers in that column are 0. Certainly appears that way to me. If a row has a leading 1, then every row above it has a leading 1 further to the left. Third row doesn't have a leading 1, so nothing to check there. Second row has a leading 1 here, and the only row above it has a leading 1 further to the left. I think that's it. That is going to be our reduced row echelon form, in fact, as is. Unfortunately, we don't really have any way of removing this negative 14 or this negative 46. If we had had like a leading 1 in the bottom row, then we could use that to help us eliminate these 2 terms. But as is, this bottom row is not going to be helping anyone out anymore because it's just plain old zeros. Add any multiple of it to any other row, you ain't doing much. So, what does that say about our initial system of equations?
Well, it would have an infinite number of solutions.
Golly. If we rewrite this, we're going to get x minus 2y plus 0z equals negative 46. Z equals negative 14. And, well, a nice pair of glasses. If you may have noticed, my glasses broke over the weekend. I still need to take them in to get them fixed. It's a sad state of affairs. But we end up with this cheeky bottom row here of 0 equals 0. So in our last example, this one, we ended up with the bottom row of something that that implied 0 equals 1. And so in that case, we said there's no solution. There's no values of x, y, z, and w that makes 0 equal 1. How many values of x, y, and z are there that will make 0 equal to 0? I would dare say all of them. This bottom equation actually doesn't really tell us anything at all. It's just extra fluff. It's something that comes out as a result of row reducing our initial matrix, but it's not giving us any helpful information. And so we end up with x minus 2y equals negative 46, z equals negative 14. And I would agree, I think we're going to have infinitely many solutions to this. Because while z has to be equal to negative 14, there are infinitely many pairs of x and y that can work along with z equals negative 14 that will satisfy that top equation. So before we move on from this, actually, does anybody have any questions so far about what we did? I made sure to check this one before class day to make sure I didn't have any boo-boos where I need to change numbers mid-fly, like last class.
In a quiz, could we re-substitute z back in earlier to one of the original? Because at that point you could use two of the original equations. Yeah, and just substitute z in, and then you just have the original or simple systems of equations.
You could if you wanted to plug in z equals negative 14 back in up here. Yeah, you could do that. I don't want to because I don't feel like trying to multiply 14 times 9. That sounds hard. Okay, fine, it's 126, but you could do that and try and solve for x and y. Spoiler alert, you'll find there are infinitely many solutions for x and y, even though you have 3 equations with just 2 variables. They'll actually, the more I talk about how much I don't want to do this, the more I want to do this. So let's actually do that. So we would get negative 3x plus 6y equals plus 14 times 9 to actually do that right.
Negative 14.
Or minus, excuse me. 14 times 9 is 90, plus 36 is minus 126 equals 12. We have x minus 2y plus 56 equals 10. We'd have negative 9x plus 18y minus 14 times 30 is 14 times 3 times 10 is 42 times 10 is 420, blaze it. Negative 6. That's right, I did just go there. I'm a professional. And if we move all our constant terms over to the same side, we would get negative 3x plus 6y equals 138. X minus 2y equals negative 46. And negative 9x plus 18y is equal to 414? Yeah. Does anybody notice anything about these 3 equations?
The first equation and the third equation are multiples of each other.
The first and third equations are multiples of each other.
And the second.
And the second. In fact, all of these equations, all 3 of them are saying the exact same thing. If you multiply both sides of this equation by negative 3, you get the top equation. If you multiply both sides of this equation by negative 9, you get the bottom equation. You really just end up with this x minus 2y equals negative 46. And then the rest of it doesn't tell you anything additional. It doesn't lead to a contradiction like 0 equals 1, like what happened in last class's example, but it also doesn't help you narrow down your solutions at all, let's say. So yeah, that's what would happen if you did this sort of substitution of negative 14 back in for z here. You would end up with 3 equations in two variables that somehow manage to all be exactly the same in the end. How do we write our answer to this?
You could write x in terms of y.
Yeah, we could certainly write x in terms of y. How would we do that?
Well, you could say x, if you're writing it in solution form, it would be x, y, z, the matrix, equals. Yeah, x, y, z equals matrix 2y minus 46, y negative 14.
Like that?
Yes.
Is that 2 minus 46? Oh, yeah, it is. I had the negatives backwards in my head. I would agree. That would be a perfectly valid way to write the solution set for the system of equations. Say, y can be whatever you want, x has to just be 2 times that minus 46, and z has to be negative 14. There's no choice about what z is in our solution set. All of the solutions have the same z. But y can be whatever you want, whereas x has to be then 2y minus 46.
Why don't we also write y in terms of x?
Because I wasn't told to. You want to try? You want to do that?
Sure.
Okay. We'll get negative 2y is negative x minus 46. So y is negative x minus 46 over negative 2. I think we could have just as validly written our solution set as something like this. X is equal to x. Y is equal to negative x minus 46 all over negative 2 equals negative 14. And that would give us an equally valid way of writing out our solution set. I probably like this one a little better just because it is slightly easier, ever so slightly, to solve for our top equation for x instead of for y. Plus this has fractions, and fractions are ooey. But both of those are equally valid as solution sets and are giving you the exact same set of x, y, and z as each other. Another way you could write this, if you wanted to feel a little more whimsical, would be to say something like this. Where here, we're writing it in sort of like in terms of like a coordinate pair, except instead of a pair, it's a triple because there's 3 coordinates, x, y, z. But essentially this and this are saying the same thing. I also chose to call the free variable t instead of y. But what you call it doesn't matter as long as you're consistent about it. Moral of the story is there's lots of ways to write the solution set to this. The book would probably have something like this and likely substitute in the t's instead of y. If like you're doing the homework, 1.2 homework, and you're looking up your answer in the back, it probably has something close to this. But either way, what that really comes down to is the fact that you were looking at a system of equations with infinitely many solutions. You may have noticed I slipped in the word free into a sentence a couple sentences ago. And I feel like I should talk about that because this is Hillsdale and we love freedom. So what you would call y in this solution, or x in this form, or t in this form, would be something called a free variable. And a free variable is just sort of a variable that you use to help denote part of your solution set, where that variable can take on whatever value you want. And you'll still get a solution, Free means it doesn't have any constraints. There are no constraints on what we can plug in for t, other than the fact that t, I guess, has to be a real number, or if we're feeling saucy, a complex number. But it's a variable that can take on any real value as part of your solution set. And typically, if your solution set to a system of equations has one or more free variables, we're going to see examples later on where there will be multiple free variables, then that usually means your system of equations has infinitely many solutions. Owing to the fact that we could plug in any value for t we want. Plug in t equals 0, negative 46, comma 0, comma negative 14 is an answer to the initial system of equations. Plug in t equals 5,000, 10,000 minus 46, comma 5,000, comma negative 14 is a solution to this initial system of equations. In essence, what this free variable does is it makes it very easy to compute, or relatively easy to compute, solutions to your system of equations by just having your solution set be in a form where you can just plug in anything you want for t and get any solution that you would care to find. But the moral of the story is all possible solutions can be written in this way. Meaning if you give me a solution to that initial system of equations, I can find some value of t, namely the y-coordinate of whatever you give me, that'll make this expression equal to your solution. Any questions, comments, or concerns related to that? It is possible to have a system of equations with multiple free variables, and I'll give you all a quick example. Let's say we had found our reduced row echelon form in the end for our system of 3 equations and 3 variables and ended up with something like this. So if this is the x column, this is the y column, this is the z column, what can we say about our solutions to our initial system of equations?
X equals 0, y is 0 free.
X is equal to 0. You forgot to mention that 0 is equal to 0.
Oh, yeah.
And not only that, but you also forgot to mention that 0 is equal to 0. But all that you would get out of that is that x equals 0. And so if you wanted to kind of write your answer in this form using free variables, a way you could do it would be to say something like xyz equals 0, y can be whatever you want it to be, z can be whatever you want it to be. Or another way would be to say something like x comma y comma z is equal to 0 comma t comma s, where t and s are both free variables that can take on any values you want independently of each other. So you could plug in t equals 1 and s equals negative 5, or t equals a billion, s equals pi. Would be different ways of getting solutions to the initial system of equations. Now don't ask me what the initial system of equations would look like that would give this. It would probably be something like x equals 0, 2x equals 0, and also 3x minus 1 is equal to negative 1. Would probably be something like what the initial system of equations would have to look like. That would give you this. And it would be up to you to even realize that there's a y and a z in the first place that are just not included in any of the information we're given. But in this case, these would both be free variables, and so technically, it's possible for a system of equations to have any number of free variables, other than the fact that you can't have more free variables than you can initial variables to begin with. If you have a system of 3 variables with an x, y, and z, you can't have 5 free variables showing up because that would not make any sense. Questions, comments, or concerns? Yes?
On the quiz, will we be required to reduce it down to row echelon form, or could we substitute a number back in earlier?
You really don't want to find that echelon form. It depends on what I ask you. I may ask you to, I may say, hey, here's a system of equations, give me the solution. I don't care how you do it. In which case I would recommend at least starting with the matrix, but then maybe you could get to here and then very quickly say, oh, those are just multiples of each other. Z has to be -14, substitute that back in, etc. I could also ask you potentially something along the lines of, here's a system of equations, or here's a matrix, find the corresponding reduced row echelon form of the matrix. In which case you would have to go all the way to the end. The reason why I ask that is being able to take a matrix and putting it in reduced row echelon form has a lot of value outside of just using it to solve systems of equations. It's definitely been the case so far that a lot of the systems that we've looked at, you don't have to go all the way to reduced row echelon form in order to be able to solve the system necessarily. But if you were to do that, it would be just fine. But I want you all to master the skill of fully row reducing a matrix, because that's going to lead to a lot of good discussion in some future standards. So the short answer is, do what I tell you to do. I like that answer. I should have just said that. Questions or comments? Congrats. That is the end of standard 1. Time for the next standard, which is going to be less computationally intensive. For those of you who are sick of dealing with these linear equations. So for the next standard, I thought is a little bit more of a getting used to the sorts of things we're going to be working with all semester long. I'm going to talk about vectors and a little bit more about properties of matrices and what can we do with them. Specifically, what are they? How can we add them together? How can we take linear combinations thereof? What does it mean to multiply matrices? If you've taken multivariable calculus, this standard is not really going to have much new from that class. Mainly because in multivariable calculus, you have to do a lot of the same things as in linear algebra in terms of manipulating matrices and vectors. We're just going to go in a different direction with using those, as opposed to, my goodness, no stealing extra packets for yourself. By the way, all packets, and by the way, now that we've finished standard 1 after class today, I'm going to go into Canvas and put my notes for the standard, including solutions, posted on Canvas. So if you want to, you can go in and see kind of what my notes were for a particular standard. If you felt like you didn't copy something down correctly, or you want to see something written that we just kind of talked about in class that you kind of forgot, those will be posted whenever we finish talking about a standard in class. And no, that doesn't mean you should just read those and not ever come to class, because we will also talk about some things that might not make it into those notes. Like I didn't include very much on free variables, for instance, in my notes. So, first of all, week into the semester and already the chalk is getting skimpy. Does anybody know what Rn is? Or if that makes you feel uncomfortable, anybody tell me what just plain old R is?
Set of real numbers.
It's a set of all real numbers. What are real numbers?
Number numbers that aren't imaginary numbers.
Really? So if I gave you the number,
Or complex.
so if I gave you the number k, would you say that that's a real number? From the quaternions?
Oh, I guess it can't be that either, but
I'm not going to answer that. Suffice it to say it's an extension of the complex numbers where we have even more bonkers things going on. Where it's like we have an I, where I squared is -1, but we also have a j and a k that do the same thing and yet are not the same as each other. It's actually surprisingly difficult to define what exactly the real numbers are. I mean, you could try and say something like, oh, it's every number on the number line. But my counterattack to that would be, how about 2? I don't see, it's not on the number line, it's down here. Is 2 not a real number?
it's every number that it's either 0 or every number that can be less than a number that can be constructed geometrically, or it could be a negative of it.
Gosh, that's a Math 105 answer. All right, I need to think about that one. It's 0 or a number that can be constructed or something that is less than a number that can be constructed geometrically, or the negative of that.
Yeah.
If I didn't want to derail the entire class, I would give a good counterattack to that, which would be something along the lines of, what about k? That's less than infinity, so that's less than a number that you can construct.
I guess.
What about 1 plus I? I could make an argument that that's less than 5. It's too early for this.
Well, what is it?
Wait, how did you make an argument? That it's imaginary.
That would be my argument. Take real and complex analysis if you want to learn more, if you want to have more debates about this as a plug. For now, I'm just going to say that the real numbers are what you intuitively think of them to be. The set of all numbers you would find on the number line, not including things like the square root of a negative number, or something you can get if you divide by 0. There are mathematical systems out there where you can divide by 0, where you can take the square root of a negative number. We are not going to be working with those for the most part in this class. If you want to take abstract algebra, on the other hand, you will be doing plenty of that. So, R is a set of all real numbers. What would that make R2? Other than the most badass Star Wars character fight me.
Would it be the square of all real numbers?
What do you mean by the square of all real numbers?
As in the set of all real numbers squared?
So that would be what, 0 and all non-negative real numbers?
Yeah.
That's an interesting way to think about it. But no, the 2 here written as a superscript does not mean an exponent of 2 like it would x squared or 3 squared, excuse me.
It's all real numbers in 2 dimensions.
All real numbers in 2 dimensions. So like that, I wrote this in 2 dimensions, assuming an infinitely skinny chalk. As opposed to that's supposed to be a 3-dimensional 2, or my attempt at it. But yeah, I would agree. R2 in general would be something we would consider to be the set of all 2-dimensional vectors, or points that have an x and a y coordinate if you prefer. So you could say the set of all, for instance, coordinate pairs, x comma y, where x and y are real numbers. So these set brackets, by the way, this is used to indicate a set. So when we say R is a set of all real numbers, think of that as we've taken all the real numbers and put them into some sort of invisible container. The container, including all of the real numbers, would be the set of all real numbers. We consider them kind of clumped together. And so R is used to refer to the set of all real numbers. R2 is the set of all two-dimensional real numbers, so to speak, where we basically say we want coordinate pairs, something that has an x coordinate and something that has a y coordinate to it. Something with multiple coordinates. So for instance, we could say 1, 2, 3, negative pi over square root of 17 would be examples of things that live in the set R2, or elements of R2. How about R3?
Is that the set of all three-dimensional vectors?
It would indeed. R3 would be the set of all coordinate triples. So the set of all x, y, z, where x, y, and z are all real numbers. So for instance, if we were to find any solution to this system of equations, would live in R3. Because a solution to this system of equations would be something like x, y, z equals something, 0, negative 14, where the something is negative 46. So x equals negative 46, y equals 0, z equals negative 14. We can consider that to be an element, or something that lives inside of R3, because it's something that has an x and a y and a z coordinate. So a solution to this system of equations would be an element of R3. Whereas something that would live in R2 would be like a solution to this system of equations. Any questions or comments so far? Let's get funky. What about Rn?
Is that the set of all vectors?
The set of all vectors?
Yes. Of any length, or any quantity of variables?
Not quite, although you're close. I think what you just described I would write as, gosh, what would I write that as? I would write it as that.
It's the set of all real numbers, from, with x to n.
With n different variables in it?
Yeah.
Yeah. So in essence, it's going to be the set of all vectors with n components, where n is going to be some fixed some fixed positive integer. So like n equals 1, n equals 2, n equals 3. But in general, when we talk about Rn, we're always going to be looking at some fixed value of n, which we can denote as being vectors that have n components to it, where all x sub I are real numbers. The reason why I hesitated to say that's different from the set of all vectors is because if you say the set of all vectors where the dimension doesn't matter, then you would include things like two-dimensional vectors and three-dimensional vectors in the same set. Whereas with Rn, we're always going to be, when we talk about vectors in Rn, we're always going to be assuming we have vectors of the same dimension. It's just that we're not specifying what that dimension is.
That x after the all, is that a subscript 1 or is semicolon?
Neither. It's actually supposed to be a lowercase I.
Oh, gotcha.
So basically saying all of the x sub I is a shorthand for saying x1, x2, up through xn, all of the different x's that we're looking at. If this it makes you feel better, you could also say all x of k's are real numbers. So maybe better, because I like the letter K. My name starts with it. And the elements of each of these sets are going to be what we're calling vectors in this class. So in general, here's where I actually start having stuff in the packet. We can say that a vector in Rn is just going to be an element or something that's contained in one of these sets. So a vector V in Rn is an ordered n-tuple A1, A2, up through AN of real numbers. So what is, Dr. Ursula, what does n-tuple mean? N-tuple is a fancy word that basically just means a coordinate pair, except pair, it usually implies two. So it's just like it's something with, it's a set of n real numbers, but in written coordinate form, is another way to think of like an n-tuple. So like a two-tuple, you could think of as being a coordinate pair. A one-tuple would just be a single real number. A three-tuple would be something like x comma y comma z equals 1, 4, 17. And so a vector in Rn is just going to be one of these ordered n-tuples. What do you think the word ordered means in this context?
It matters which order the numbers are given in, so you can't switch them around and it's the same vector.
Yeah, exactly. So what this ordered is saying is that, for instance, 1, 2 as a vector in R2 is not the same vector as 2, 1, even though they include all of the same pieces, a 1 and a 2. The order in which you write the numbers matters for determining whether you have vectors that are the same or not. So, collection of all these vectors is what we're going to be calling Rn, and an individual thing living inside of Rn is going to be called a vector in it, for the purposes of this class. And vectors and matrices, going forward, are going to be everything that we do in this class. Meaning there's going to be almost nothing that we talk about over the course of the rest of the semester that's not going to either be a vector of some sort or a matrix of some sort. Where we're going to talk about what's the relationship between a vector and a matrix. You could probably already start to guess something about like, oh, a matrix is made up of vectors in rows or in columns, so to speak. There's oftentimes 3 notations that you'll see being referred to vectors. You might see a bold-faced V, which I think our textbook sometimes uses, and is what I often will use if I'm typing it out. You might see a V with a little hat on it, and you might just see a plain old lowercase v. No bold, no hats. It's out in the cold, it's getting snowy. My mind goes to great places. These two always mean the same thing and are going to be used to refer to vectors. Please, 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 if you are handwriting something on a quiz or an exam, use that, don't use the bold-faced V, because it's very hard to read boldface in handwriting. On the other hand, if you're typing something up, like what's in our textbook or in my notes, you'll oftentimes see the bold-faced V being used to refer to a vector name. It means the same thing. This is a lot less ambiguous, though, when things are handwritten. If you see a V by itself, usually that's referred to a scalar. Somebody tell me what a scalar is?
Number.
Just a single number?
Yeah.
That is correct. For now. Later on, it's going to mean something else, but for the purposes of what we're doing, a scalar is usually going to refer to something that's just a single number, or if you prefer, a vector in R1 specifically, as opposed to something that's going to have multiple components to it. And I know it feels like we're going really slowly, but these are going to be super, super important to us going forward, and I really want to hammer down what the difference is between these things so that you all feel comfortable working with them. And we're actually going to leave it there for today, but when we come back on Friday, we're going to talk about how can you represent a vector geometrically instead of just using numbers. How can you draw a picture of a vector, which you've been doing your whole mathematical careers without probably realizing it. We're also going to talk about what can you do with vectors? How can you combine vectors, multiply vectors by scalars, and then talk about how to do the same things with matrices. But first, at the beginning of next class, we will have our Standard 1 quiz. By the way, if any of you want to come in and retest Standard 1, I'll let you do that before the Standard 1 quiz, so you can get in your retest for the week. If you're interested in doing an outside of class version of the Standard 1 quiz, send me an email and give me some times that you're available, preferably during my office hours if possible, and I'll be happy to set you up for a retest in the next couple of days. Have a good one. You get to keep that. If you go on campus right now, it probably still shows that. No, it's not probably. Your score will still show a 0 for Standard 1. That's just because I update Canvas once a week with my grade, but you got that next.
Thank you. Can I come
You betcha. Go ahead and send me an email just so I know you look at it.
Thank you.
No problem.